Okay, let's do kind of a quick review of the topics from our previous module. So we were looking at the idea of complexity, and our end goal is if we're given more than one algorithm, we want to identify which is better. But in order to answer which is better, we have to identify what we're trying to compare it against. It's better for what. And in this class, we're really looking at two main concepts: the amount of time something takes and the memory used. And remember, for this notion of time, we're actually using the idea of a fundamental operation, a constant time operation. That's really just an approximation. So the approach that we're going to take is we're basically going to do some form of accounting or counting. We'll develop equations that somehow are a stand-in for the amount of time or memory being used. We're also going to be using these this idea of big O, big omega, or big theta approach to do our comparisons. So let's do a quick review of that. So there's some limitations to this approach. So just as kind of a quick reminder, remember that all three of these kind of represent a set of functions that are all considered to be members of the set because of properties of those functions. This approach to comparison is actually focused on growth. If you remember, there was this idea of being past a certain start point, so n greater than or equal to n0. So what we're really focused on is what happens as our problem size increases, and getting to some crossover point where we can clearly say that one thing is bounded by another, and our three different types of functions, O, omega, and theta, are different forms of those boundaries. Okay? Kind of implicit in this idea of being past some sort of a critical startup point is the idea that this isn't exactly the right choice for comparing small problems. So when we're doing these comparisons, sometimes the big O notation or the big omega or theta notations will give us an indication that one algorithm is better than another, but it's really about being better past this particular point. And also, this isn't very useful for things where the notation essentially boils down to the same formula for multiple choices. If you remember, this glosses over fine-grained details of how code actually executes. Even though we might have multiple constant time operations, a constant time operation on one computer may actually be faster or slower than a constant time operation on another computer. And subtle differences like that aren't taken into account for this approach. But this is still really useful. It allows us to compare algorithms, and if an algorithm has a significant benefit, it will be revealed in the big O notation. Okay, so let's do a quick review of the definition of the big O notation. So what is it? So we're always talking about comparing multiple functions. So our notation is using f and g. They're non-negative functions, so that kind of makes sense for time. Our memory, these are things that can't be negative. And we're interested when n, our problem size, is greater than 0. So here's kind of a graphical representation showing the relative positions of two different functions, and this plays into the second component of our definition here. So the second component of our definition is really explaining when we would consider f to be in the big O of g. So again, there's some sort of a startup point, a crossover point, which is called n0 and kind of represents this point. And what we're really focused on is what happens to the right of that. Okay, so again, this is really all about problem growth. As n, the size of our problem, gets bigger and bigger, we're not really interested in these things that happen when the problem's small, but we're interested in what happens as the problem continues to grow. So we would say that f is in the big O of g if, after that startup point, f's value is always less than some multiple c times g's value. So what that's really saying is that there's some way to take our function g, multiply it by something, and that will always be above. It will bound f from above. In kind of practical terms, what that really means is that we can say, oh, f is better than some worst case. We can kind of bound it and say, well, it will be no worse than this. Okay, so that's kind of the definition of the big O notation. The big O is about having a bound above our function. Okay, and again, we kind of ignore the startup point, and we're really focused on kind of this growth area here after that. Omega is just about the opposite. it's about having a bound below. So again, we're comparing one function to another. We're still focused on non-negative functions and an n that's increasing, a problem size that's increasing. We say that our function f is in big omega of g if there's a constant c, such that after some startup point, f is always above some constant times g. So in this case, again, f is above g. So this is about establishing a lower bound. Okay, so we can say that f is always greater than or equal to the omega. Okay, our third option is theta, and this is about a precise boundary. So it's kind of similar to the idea of being equal to something. So still we have our concepts of f and g, non-negative functions on n, and we say that f is in the big theta of g if there exists constant c1 and c2 that can be used to bound it from both below and above. Okay, so again, our three notions, big O, which is about having a bound above, big omega, which is about having a bound below, and big theta, which is about being bounded both above and below. So we also looked at how we could do some proofs for all three of these, and our basic overview breaks down into a couple of different components. We were always relying on the definitions of these. We were picking the constants that were involved in those definitions, our c and our initial start point n0. And we were trying to prove the equality that are inequalities that were inherent in the definitions. So we did those proofs by using arithmetic, algebra, and in some cases a little bit of calculus. And on that front, is there a more uniform approach? So today we will continue to look at using the notion of calculus to give us another approach to proving when one function is either in a big O set, a big omega, or big theta.